Hello everyone, today I'm going to present an overview of our proposed system called mmLSH, which can efficiently index and retrieve multimedia objects such as images. I am Omid Jafari, and along with my co-authors, this work was done at New Mexico State University. In this paper, we look at the problem of finding similar multimedia objects to a given object. Often, a single multimedia object, like an image, is represented as a collection of features, such as a collection of sift features, as shown in this slide. The tiny circles in each image are the sift features of that image. One common way to find similar images is to use approximate nearest neighbors techniques, such as the popular locality-sensitive hashing, to find nearby features for each sift feature of the query image. In order to do this, a top-k feature query has to be executed on each feature of the query image. The result of these feature queries are then aggregated using techniques such as the board count method. And board count method gives scores to each image in the database based on how many features belonging to that image appeared in the top-k results of the query image. There are two main drawbacks of this approach. One, the theoretical guarantees are on the results of each feature query, and not on the results of the overall multimedia query object. That is, the theoretical guarantee will be on the nearest neighbor points for each sift feature in the image, but there are no theoretical guarantees on the results of the query image. Second, each existing technique treats these individual features as independent of each other, and hence cannot leverage common elements between these feature queries for improved query performance. We propose a technique called mmLSH that solves these two drawbacks. mmLSH can efficiently solve approximate nearest neighbor queries on multimedia objects. We provide theoretical analysis and guarantees on the accuracy of the result of a given multimedia object query. Finally, we propose intelligent buffering strategies that help us further improve the performance. This slide shows the overall architecture of mmLSH. Each of the modules shown here will be explained in detail in the next slides. The module that is gray highlighted uses existing LSH functions from state-of-the-art LSH techniques. The Gamma Analyzer module monitors the number of nearest multimedia objects. Existing techniques focus on finding nearest features, but our technique focuses instead on directly finding nearby objects, which as a result help us to stop the algorithm earlier, hence saving time. We also have a buffer-conscious optimizer, which is an optimized buffer utilizing a novel eviction strategy. We will first describe the Gamma Analyzer module and then briefly explain what the gamma distance is and the two terminating conditions, which help us give guarantees on the query results. In order to give theoretical guarantees on an object query, we have to define a distance metric between two objects. Note that there have been several works that have defined voting-based similarity distance measures between two multimedia objects, especially images. Also, region-based algorithms have been explored in the past, whose main strategy is to divide the query object in regions and compare these regions of the dataset objects via some region distance, and then aggregate the resulting distances. In this work, in order to give theoretical guarantees for our results, we propose a gamma distance measure that compares all pairs of features of the objects, but it uses a user-specified percentage parameter gamma to ensure two identical objects have a near zero distance. In our paper, we present the corresponding definitions of collision index of two objects, gamma candidate objects, and gamma false positives. Due to time constraints, we do not present them here. We ask the viewer to refer to our paper for those definitions. Existing solutions terminate when top k prime candidates for each query feature of the query object are found. mmLSH instead stops when top k objects are found. mmLSH has two terminating conditions in order to find top k objects given a query object. First, at any time during query processing, if at least k plus beta s gamma candidates are found, where beta s is the user-defined allowed number of false positives, and second, at the end of processing each radius and before increasing the radius to find more nearest neighbors, if at least k gamma candidates whose gamma distance to the query are at most r are found. These two conditions guarantee that gamma c square approximate nearest neighbors are found with constant probability. We ask the viewer to refer to our paper for rigorous proofs for these guarantees. We will now explain our novel buffer-conscious multimedia query optimizer. The goal of this module is to leverage common elements between feature queries and devise an efficient eviction strategy that will lead to faster overall query processing time. We will first show how a naive buffering strategy such as LRU will work in the context of LSH queries on multimedia objects. In this naive buffering strategy, we first find the hash bucket locations for each of the point queries of Q, which are Q1 and Q2 and Q3 in this slide. To make the LRU eviction strategy more effective, in each projection we order the execution of point queries according to the hash bucket locations from left to right. And whenever the buffer gets full, we evict the index files from the buffer based on an LRU order. As an example shown in this slide, the queries are processed with the order of Q1, Q2, and Q3. With an assumption that the buffer can only hold one hash bucket, we can see in the animation that this eviction strategy is not efficient since, for example, bucket HB2 is being retrieved 2 times from the disk, while it could have been stayed in the buffer to save I/O. In order to utilize the buffer effectively, we split the queries into multiple subqueries and reorder the execution based on these new subqueries. For example, in this slide, each query is divided into 2 subqueries, and the order of execution is based on those subqueries. With the same assumption as the LRU strategy, we can see in the animation that by using this strategy, there are more overlaps with items in the buffer now. Therefore, a hash bucket, which is brought into the buffer by one query, can be used by several other queries before the bucket is evicted. The main challenge in this approach is to find a good splitting factor. Choosing the splitting factor is a trade-off between algorithm time and I/O cost. An overestimation of the splitting factor can lead to having a lot of subqueries that will increase in algorithm time. And an underestimation will make this strategy close to LRU and result in more I/O cost. We empirically find this best value of the splits for our experiments. Additionally, based on our observations, we design our buffer-conscious optimizer based on 3 eviction criteria for each hash projection bucket. First, if the bucket was not added very recently, it will be evicted because for newer buckets, there is high likelihood that another query might use them in the near future. Second, if the bucket is far away from the current query, it will be evicted because it is likely that the next query is close to the current query and thus require nearby buckets. And third, if the number of queries that still require the current bucket, which we call the frequency of the bucket in the next slide, is the lowest, the bucket will be evicted. This criteria will ensure that a bucket needed by a lot of queries is not evicted. While the first 2 criterion can be naively solved using an LRU policy and a hash map that keeps track of the bucket locations, the third criterion requires us to calculate the frequency of each bucket in the online processing phase, which is a time-consuming task. Therefore, we present a projection dividing strategy, which is explained in the next slide to overcome this challenge. Our strategy to solve the challenge of estimating frequencies is to split the projections into different regions. Then we calculate the number of buckets in each region which are required by the queries in the same region. For example, in the first region of this figure, buckets HP1 and HP2 are needed 3 times by queries Q1 and Q2. We call this number the frequency of that region. Finally, we assign the frequency of each region to each of its buckets, and we call it the approximate frequency of each bucket. For our example, the approximate frequency of HP1 will be 3, and approximate frequency of HP2 will also be 3. Therefore, instead of having exact frequency for each bucket, we will use the frequency of the region as the approximate frequency of the bucket. By doing this strategy, we can make sure that we would be able to process the frequencies and calculate the frequencies in the offline phase, and use random queries in the offline phase to estimate the frequency of each region. We compared the exact frequencies for the real queries with exact frequencies of random queries and also approximate frequencies of random queries in one projection. And the chart on this slide shows how close our approximation is to the actual frequencies. As a result, the challenge becomes in choosing the correct number of divisions for projections. Too many divisions will lead to an error between estimated and actual frequencies, because then the random queries can be far from other regions and not be able to be good estimators for the frequencies. And too few divisions will result in a high error between estimated and actual frequencies. In order to evaluate the effectiveness of our proposed method, we compared mmLSH with 3 different techniques, namely linear search, C2LSH, and QLSH. We used the board account strategy on top of these techniques to aggregate their results in order to find top K images. We used 4 commonly used image datasets in our experiments with different sizes and different feature extraction methods. Our goal by proposing mmLSH was to efficiently find top K approximate nearest neighbor images, and to evaluate mmLSH and compare it with other methods. Therefore, we used 2 criteria: the execution time, which shows the time it takes for the technique to find top K multimedia objects, and moreover, similar to the ratio defined in state-of-the-art techniques, we defined an object ratio to calculate the accuracy of the returned top K objects. Object ratio of 1 means 100 accuracy, and as object ratio increases, the accuracy will decrease. In this presentation, we only show the results for the datasets in bold and refer the viewers to check the paper for the complete results. As it can be seen in the charts, mmLSH always returns a higher accuracy than alternatives, while being much faster than all three alternatives. This is mainly due to the fact that mmLSH is able to leverage the common elements between queries and improve performance by utilizing a buffer, while also being able to stop earlier than state-of-the-art techniques. The times in these charts are in log scale because we found that QLSH is significantly slower than other techniques. In conclusion, we saw that state-of-the-art techniques consider each single feature of a multimedia object individually, and thus suffer from slow query processing and low accuracy. To alleviate these problems, we presented a novel structure to efficiently perform similarity search on multimedia data using locality-sensitive hashing, which we called it mmLSH. mmLSH considers the common elements in each multimedia object and provides terminating conditions based on the top K objects. Furthermore, it utilizes an efficient buffer-conscious strategy to further improve the execution time. As the last step, mmLSH provides rigorous theoretical guarantees to prove its efficiency when used for multimedia applications such as image processing. Our experimental results on real datasets also showed the benefit of mmLSH as compared with other state-of-the-art approaches. Thank you for attending our presentation, and we hope you'll find the information useful, and in case you wanted to contact us, this is our contact information. Thank you for your time.